Hello and welcome to lesson 3 of calculus and vectors, where today we are looking at instantaneous rates of change after you familiarized yourself with average rates of change in our previous lesson. And I hope you got a chance to explore Fibonacci sequence and how limiting values exist for specific sequences. And today we're also going to be looking at how those limiting values exist when we are exploring secants and its connection to tangents of graphs. So our learning goal for today is to define instantaneous rates of change using graphs and tables and to connect the slope of a secant line approaching a tangent line to determine that tangent line as well. So starting with some definitions, we have tangent to a curve. So this should be a reminder from last lesson. So a tangent to a curve is a straight line that intersects the surface at exactly one point. And the tangent to a curve at point P just specifies that exact point for us. So you're given a point and you're asked to find the tangent for that point specifically, as compared to finding the tangent to any generic point. So in this little diagram here, we have 4 different points shown on the graph of function y equals f of x, and the tangent of each has been drawn. And you can see that while it does look like the red lines, the red tangent lines are intersecting or intersecting the blue graph in a lot of points, they actually only intersect at one specific point. For example, here might be this point here. And if you go really close, if you zoom in on these graphs very close to those points, then you will see that they actually only intersect at those one single points. So again, remember our goal for calculus is to find out what those lines are by finding the slope and calculating the equation of the line given the slope. And we have the point as well, so using the slope and the point. So to do that, we're first going to consider 2 points, point P and point Q, on a curve of the function. And this is also a refresher definition for us, but a secant is a straight line that intersects the curve at 2 or more points. And if we have point P and Q, then the secant of point P and Q, or secant PQ, is the line that connects these 2 points on the curve of the function. So looking at our diagram here, we have for the blue function y equals f of x, 2 points P and Q, and generally with notation, P is our main point that we're looking at because P and point, and Q is our second point that we chose. So P is the point that is our main focus, and if you see on the diagram, we're also considering tangent at P, but we choose point Q to help us through this process. So point Q can be any random point. So here you can see this specific point chosen on the graph, but it can be any point on the graph as well. And so as we choose Q that such that it's getting closer to P, the secant of PQ or the secant PQ actually starts to resemble the tangent at P. So pretty much if you start getting closer and closer and closer from point Q to point P, then the difference between those 2 points is going to be so small that that secant is going to resemble the behavior of the tangent. And so the slope of the tangent, and pay attention to this specific wording here, because we're going to be using it very soon, is the limit of the slope of the secant as Q approaches P along the curve. So as, again, remember, Q is approaching P, we are calculating the slope of the secant, and the limiting of the slope is going to give us the slope of the tangent. So the slope of the secant represents the behavior of the graph as it approaches point P. Now, connecting that to the definition of slope of a tangent, so it is the slope of the secant PQ as point Q gets closer to the point P on the curve. So let's try an example. Consider the function f of x with as x squared, or a parent function of the quadratic, and we have the point P as 1, 1. And we are asked to determine the slope of the secant through P and Q for these points. So I'll try one example first to start us off. So for this one, we have M, and remember this is the change in Y over the change in, oh, over the change in X. And let me add actually this part for you. So this is y2 minus y1 over x2 minus x1. And really, it doesn't matter which one you choose as y2 and x2 and which one you choose as y1, x1. You can set this one, or sorry, x1, y1. You can set p as x1, y1 as a general rule. Or I typically start with the bigger one as my first one so that I'm getting a positive outcome for my subtraction. But again, your value should not change regardless of which one you choose. The key thing is if this one is y1, then it's also x1. And if this one is x2, then this one has to be y2. So here we will calculate this, and feel free to use a calculator here, especially because we have a lot of different calculations. And 1.5. And this will give us 5 over 2, or 2.5. Now, I'll give you a moment to try the rest of these and see what you get. So for the first three, you should have got these now. And I just wanted to show you briefly this one because I'm actually, again, going to change the value or the order of x1 and x2 so that I end up with a positive outcome. So here, I'm just going to do m as this time 1 squared, or f of 1 minus f of 0.9 over 1 minus 0.9. And so if I try this, I should get 1. I'll get 19 over 10, or 1.9. Okay, so try the next two and we'll be back shortly. Okay, so that's all the slopes that you should have got. And now let's take a look at what that might look like. So consider our function f of x for x squared. And the point we have is this point here, okay? And this is 1, 1. So starting with that 1.5, 1.1, 1.01, and 1.001, that means that if you start at this point, which is further along on the number line or to the right of 1.11, and you start to approach by moving more left on the x-axis, then your x value is getting closer to 1. And you see that the slope is getting closer to from 2.5, 2.1, 2.01 to almost 2. Now, from the other side, if you start at 0.9, so somewhere from the left of the parabola, and draw the secant and again start to go closer, closer, and the x value is approaching 1. But now from the left-hand side, then we see that our output value is also getting closer and closer, so that the slope is giving us 1.9, 1.99, 1.999, and that one is also getting closer to 2. So what can you conclude about the slope of the tangent to the graph of the function at point P11? We can conclude that the slope of the tangent would possibly be 2, as we can see that the behavior of the secants, which resembles that behavior of the tangent, is from both sides getting closer and closer to 2. So now here, I want you to take a moment and pause the video and this lesson, and you're actually going to try the practice set that has been posted for you, practice set number 3, which is slope of a tangent, where you're going to be doing the same practice, but with another point to see if the same pattern happens, or if is this pattern simply because point P11 is a special point, and also to determine if you can find the slope of the tangent for another point on the quadratic. So take a moment to try that, and I'll be back with you shortly to complete the lesson. So by now you should have got two sets of practice determining the slope of secants with specific points in order to determine the slope of a tangent at a specific point. So in the first one we just saw was the example of point 1, and you just got to practice another point in practice set number 3. So now let's try to generalize that. So we're working still with the same quadratic function, and now we're told we have the point P39. And for Q, you're given a generic point, so it's not a specific point, but it's a point that's going to be h away from 3 on the x-axis. And whether h is positive or negative, you can be moving more to the right or the left, and we'll see the case for both. So first, let's try to find an expression for q, which we already have that 3 plus h there, so we want to find 3 plus h squared. In order to find that m, which is the difference of our y over the difference of our x. And let me just fill this out. This will be um, squared minus just 3 squared. And in the denominator, we have 3 plus h, which is our first x, and subtracted from 3. So if you try expanding this now, in the numerator, we have 9 plus 6h plus h squared minus just 9. And then in the denominator here, I'm going to just simplify that. So we have just h, because the 3 minus 3 is canceled out. And here in the numerator as well, that 9 and then minus 9 cancel out. So we're left just with h squared plus 6h over h. And this is also, if we factor out the h to get h plus 6 over h, then our m is essentially just equal to h plus 6. But we don't know what h was, so h can have different values. And for example, if we start at h is 1, then we're looking at the point q for 16. And we can see that the slope between those two lines, or those 2 points, would be, since h here is just 1, it would be 7. But let's say we kept picking q so that the points are getting closer and closer to 3. So let's say we picked h as 0.5, then we picked h as 0.1, then we picked 0.01, and so forth. So we're decreasing. And here we're approaching the parabola. So if we have our parabola with 0.39 there, we're approaching from the right-hand side and decreasing the values. So our x is getting closer to 3 from the right-hand side. Alternatively, we can consider h as -1 so that we have the point Q24. And here we can also now consider h as -0.5, -0.1, and -0.01, so that we are getting closer to 3 now from the left-hand side. And as we get closer from both sides, from the both left and right hand side, we see that our values should be getting closer to the same value, just as we saw in the 2 examples above, where in the example here we were getting closer to 2. Here we'll also be getting closer to a specific value. So consider h is getting closer and closer to 0, then what do you think would happen to m as h is getting closer to 0? So specifically, as h approaches 0, which we write with an arrow, what would happen to m? And I hope that you see that m is actually getting closer to 6. And so here, the question that you're asked, how can you use the slope to determine the behavior of the tangent to the graph of the function at point 39? It's pretty much the explanation I just gave. So that if you are getting closer and closer, the slope of the secant start to resemble the slope of the tangent. And as you pick points for Q, or you specifically pick H such that Q is getting closer and closer to point P, then we can see that those secant slopes are going to be a very good representative of the behavior of the tangent. And so, as we just established, that should be closer and closer to 6. So here, just to put that into mathematical language, so the slope of the tangent to the graph of the function f of x at point P, and here we are generalizing now, so point P, x, y, and this can now be any function. It doesn't have to be a quadratic function here as well. So this slope is the limiting slope of the secant line PQ. So as point, this is just that same Q we saw, but now generalized with x, and in the output we have x plus h squared. So this one is for the quadratic, so it's giving the quadratic example. So as we slide along the parabola and approach point P, so Q is getting closer and closer to P, then that means H is approaching 0. And we can write this limiting slope using this limit sign now, where we are saying that the limit as H approaches 0 of that M value, and we're going to find what that is. So the slope of the tangent at point P is the limit of the slope of the secant PQ as H approaches 0. So in our case, this was the slope of the secant was M H plus 6. So as H approaches 0, then we're actually just approaching 6 for the value of the slope. Now let's look at a next example where here the function f of x is equal to x squared, so the same parent function of the quadratic is given to us. And now we're just filling back what we just did up there with our limit using mathematical notation. So this is the same part we just found up there, the change of y over change of x, which we found is 6 plus h. And so as h approaches 0, 6 plus h approaches 6. And so the limit, oh, this should be a 0 there. The limit here will be just 6. And so we can conclude that the slope of the tangent at 0.39 of the function y equals x squared is 6. And so this over here would be your complete solution. And you can see it's much more minimized since we're using mathematical language and not explaining our solution like we did up here. And we still got that same answer of 6. So now generalizing that to any function and any point P, we have for a function y equals f of x, and this can be quadratic, it can be a trigonometric, it can be exponential, any function. Choose any random point. So our point is now represented, again, because this is a specific point, we don't use x and y, we set x to be a specific value. So x is set to a, so our specific point is going to be p of a, and the output is just f of a. And any other point, q, which is this one, is going to be our x and y since it's a general value, but soon we're going to change that. And we pick Q specifically so that it has a horizontal distance of h away from P. So you can see in this diagram here, h here is positive, so Q ended up to the right of P, but we also discussed the case where h is negative and Q might end on the left-hand side of P. And so with that in mind, we now have that same representation of Q, which is a plus h for the input, and then the output is just determined by the function. And so here we have the secant between P and Q, and they've drawing for the tangent of P as well. And so putting that all together, we're now going to be approximating the limit of the secant of PQ as Q gets closer to P, or as that horizontal distance h approaches 0, so that the point Q is getting closer and closer to P. And the slope of the secant now, using that this terminology or this mathematical notation is just represented by f of a plus h, take away f of a. And in the denominator, we also have that a plus h minus h, which simplifies to h. And now this value here, this fraction is a very important fraction. This is called our difference quotient, and you're going to be seeing this a lot throughout calculus. So please get familiarized with it in this lesson and the next. And if you have any questions, please reach out because this is one of our very important key concepts. And so that being the slope of the secant, then we can have our new key idea here, which is the slope of the tangent, is now that same slope, but with a limit, which is the limit as the change of x approaches 0, or again, that horizontal distance decreasing, which is the same as if h was approaching 0 in our difference quotient. And this has to be true if this limit exists. So soon we'll look at when that limit might not exist. But for now, through substitution, we should be able to find the limit of these next few functions. So consider this function y equals negative 2x squared minus 3x plus 5, which is another quadratic. And we're asked to find the slope of the tangent at point x is equal to negative 2. And we're also going to sketch the graph and the tangent after just to make that graphical connection as well. So from the definition above, we first find f of negative 2 because that's our a here. So here, this is actually a as negative 2. And so f of a, which is f of negative 2, which we find through substitution, is just 3. Now, here, considering that a is negative 2, then our point Q, so P is negative 2, 3, then Q is negative 2 plus H, and let's say this is function f of x, then this is negative 2 plus H, which we'll find through substitution, but I'll show you that shortly. So over here is where we do the substitution. So my output of this function for an input of negative 2 plus h is going to give me, and this is just the function, I've copied it down here with the negative 2 plus h input substituted wherever we had x. And if you simplify this, and I recommend you try this on your own, you should get negative 2h squared plus 5h plus 3. Now, the slope of the tangent is going to be given by the difference between this output and 3 over just h, because the difference of these two inputs is just going to be h. So here, I've shown you there, or actually, I can show you briefly here. The slope of secant would be that negative 2h squared plus 5h plus 3, took away 3, over, and this is negative 2 plus h, minus negative 2, which will just, this part give us h. And if you look over here, this is now the slope of the tangent shown by m, and this is that same thing here, the same fraction, but with that limiting behavior where h is approaching 0. And so if we clean this up a little bit more, we can factor out that h, which simplifies my denominator. And I want you to think here why this part is important. And if we don't do this, then substituting for h is approaching to 0 would require me to have a denominator of 0, which is not defined. It's not something we want to be working with. So that's why I have to factor out that h so I can simplify and get rid of that 0 denominator. So canceling those two out, I am just left with negative 2h plus 5, which as I see that as h approaches 0, then so does negative 2h. And so this whole thing will eventually just converge to just 5 because this value is just going to be 0. And so now, again, I suggest you try this part here as well, where we have the slope and you have the point -2, 3. And I want you to show that the equation of the tangent will be y equals 5x plus 13. So this is essentially just using y equals mx plus b for m equals, where did I have m? Oh, m is 5. And you should get that by substitution, b will be 13, which should give us this equation right here. And this is now the graphical representation of these two functions. So with the red, we have our quadratic function, and this is the point -2, 3. And again, here, even though I've zoomed in quite a bit, even including on Desmos itself, you see that it still kind of appears that close to the point, the blue line is intersecting the quadratic at different points, but it is actually just intersecting it truly at that one point of -2, 3. And if we zoom even closer and closer, we'll see that it should not connect. And here we can confirm that we have that slope of 5. And this is the tangent of our quadratic function at a specific point for the point -2, 3. Now let's try another example without quadratics. So just to see a variety of functions, because throughout this course we are going to be looking at other functions that are not just polynomials. So for this root function of just our parent root function, which is square root of x, we want to find the slope of the tangent at x is 4. So here we also start with just setting here, remember a is 4. So then f of a is square root of 4, which is 2. And point Q here is going to be a plus h and square root of a plus h. And that's just substituting into the value of the function. And so here, if we get this limiting value, and one thing here, it's easier for me because I already have 4. So here I can just write 4 plus h and 4 plus h. So substituting for the slope of the tangent, I have m is equal to my limit as h approaches 0. And I'm taking the difference of the output, so f of 4 plus h minus f of 4 over h. And that's my difference quotient. Now here, simplifying that, I have 4 plus h, square root of 4 plus h, minus 2, which was the f of 4, over h. And we want to find, again, what this limit is. And again, consider here, as h is approaching 0, I cannot have a denominator of 0, so I need to find a way to get rid of that h. And here, having that square root, I hope you remember what we saw in our first lesson of rationalizing. And here we actually have to rationalize the numerator, which is okay. Sometimes we have to do this as well. So rationalizing the numerator, and I want you to think what the conjugate here would be. So think of this as my first term, or let me highlight it. This is my first term and this is my second term. Then I want to keep those. So 4 plus h and the 2. And because they're being subtracted here, I'm just going to add them. And then I need to keep my fraction the same so that it equals to 1. And so we will multiply by this conjugate and take a moment and see if you get the same answer, which is shown over here. So here I am multiplying by the conjugate. And in my numerator, I will get that this 4 plus h and this 4 plus h will just become 4 plus h with no square root. And then the inside terms will cancel out because I'll have a positive 2 of this bracket and a negative 2 of the bracket. And then my last term is just negative 4. And in the denominator, I just have that 4 plus h plus 2. And here, this is okay as h approaches 0 because as h approaches 0, this whole thing does not give me a denominator of 0. So then I can work with this. It's okay. Now, in the numerator here, 4 plus h minus 4 is just giving me h. So that h and that h cancel out. And now I will just solve my slope using substitution because I can do that and it will give me a correct value. And if you substitute, you see that this just becomes square root of 4, which is 2. And so our final value or our slope is just 1 over 4. And so our concluding sentence here, we can write the slope of the tangent to the function f of x is equal square root of x at x is equal to 4 is m equals 1 over 4. And if you were asked to find the equation of the tangent, you would just have to use the point. So let's define our point as P 4, 2. Knowing that m is 1 over 4, you can find y equals mx plus p, and this will just be the equation of your tangent, but here you're just asked to find the slope. So please make that distinction of whether you're asked to find the slope or the equation, because one will save you some time if you're just finding the slope. And now, this we saw last class of average rate of change, but now we're putting it together with instantaneous rate of change. So if you remember, the average rate of change was our was the secant of the 2 points, and this in context with speed and velocity is our speed and velocity. So with consideration to movement, horizontal movement, this is just velocity and speed, and it's given as the change of the position of the object with respect to the change in time. So how much does the object move in position with respect to a given time difference? And that value is going to be our speed or velocity. We can also have now the instantaneous rate of change. So what the speed or velocity is at a specific point, and this is now our tangent value. Or specifically, the velocity at a particular time t is equal to a is calculated by finding the limiting value of the average velocity as h approaches 0. So pretty much that same connection between this one being secant and this one being tangent. And just putting that with the correct terminology here, since we are using S and T, we say that V of A, and this is the instantaneous rate of change at a specific point. If we were doing the general, we would have V of T, and this would be, the only difference would be here at the end where we have instead of a, we would just have x plus h minus s of x, and this would just be over h. Let me just move this over so you can see it there. So instead of a, we would just keep it as x. But because you're told at a specific time, so time a, then we have to include that a in there and find the limit for that specific a. So let's look at an example with specifically with movement, where here a toy rocket is launched straight up so that its height s in meters at a time t in seconds is given by the following function. And we're asked what the velocity is at time t equals 4 seconds. So here, first we want to find s of 4. So substituting into our equation, okay, so I'm just going to try this. This will be 42. So that my point P is 442, and my point Q is 4 plus H and F of 4, or sorry, S of 4 plus H. And so here I'll also find what S of 4 plus H is. And this will be -5. So everywhere that I had that T, I'm now going to substitute in this new expression. And so I'm doing my simplification now so that after when I substitute in my limiting function, then it's a little bit easier. Or here we have 16. squared. Oh, sorry, this should be plus 4 plus h. So 20 plus h plus 2. And now substitute or distribute the -5 in there as well. Just copy these. And now we are going to collect like terms. So I only have one square -15h 42. And now I can find the velocity, which is, maybe let me add one more page here, just so I can show you. So then my velocity is given by the limit as h approaches 0 of, so remember it's s of 4 plus h minus s of 4 over 4 plus h minus 4, which in the denominator, this is just h, and then for our numerator, we have, and never forget that limit there. I know we're not used to it with equal signs, that there's something else that follows directly after, but with limits, practice writing that limit right away so you don't miss it. So we have minus 15h, 42. And then my S of 4 was just 42, which actually works out great because I can already see that 42 minus 42 is going to cancel out. And so here I am just left with, and I'll just factor out the -5h. So then I have h plus 3 over h, and these two will cancel out. And as h approaches 0 here, my bracket itself will become 3, but I do have that -5 I have to account for as well. So this becomes -5, 3, or -15. And now this tells me that my velocity is negative at t equals 4 seconds, which could mean that I am speeding down here. Sorry, to correct myself, it does not mean that you are speeding down here. It means that you are moving in an opposite direction than what is expected. So consider a toy rocket that launches straight up. Then the position that we are counting as positive is when the rocket starts and it's going upward. Then that would be our positive positive velocity, as we say that we are moving in the direction that we want. Versus when the rocket is coming down, we're now working in the or moving in the opposite direction as we are moving down towards the ground. And so in this case, we can say that the velocity is negative here, where the 15 would be our meters per second. So we're moving at a speed of 15 meters per second downwards, or in the opposite direction, which in this case is downwards. So then at time t equals 4 seconds, our rocket is moving towards the ground at 15 meters per second, which the units I got from the question itself. And I just wanted to show you this graphically as well. So this is just the function s of t graphed on Desmos, and we can see that the rocket starts at a height of 2. It goes upward and reaches a maximum height of 47 at time 3. And so by time 4, which is approximately here, we are approximating that the object is moving now back downwards towards the ground, and the speed that it has would be the speed of 15 meters per second and moving downwards. And for example, I hope that you can see that for point 2, time equals 2, we might have a similar speed, but now our velocity will be positive since we are moving upwards still in the direction that the rocket started. So that is moving upwards. Other examples of this might be when you're thinking of a car that's moving. So if a car is moving to the right, then anytime that the speed is positive, it's moving in that same direction. But when it becomes negative, the velocity is negative. That means that you are maybe moving backwards. That could be that you are reversing, or it just means that your car's turned around and you're now moving to the left. You're driving to the left. And that is the end of our lesson for um, lesson 3 on slope of a tangent. You do have some practice problems and at the end of this lesson to give you a try. You have done the practice set already, so just work on the practice set questions as extra practice. And as always, if you have any questions, please don't hesitate to reach out.